So it is Monday morning and we are in the studio and we are filming after our frightening hair frying Friday. Literally hair frying. Yes, that was not a good day. I will tell you one thing. If you're doing math and you have a candle lit on your table, make sure to keep your head away from the candle. Because if you're like me, there is a high probability that you get really into your math and you need your forehead like 3 inches from the paper, and that means your hair is like right next to the open flame and it's not very good and it smells really bad when you get your hair on fire. So anyway, it's a little bit of Monday morning advice to myself. So we are starting today off by learning how to graph the cosecant, secant, and cotangent curves nice and easily. We're going to start by graphing the cosecant curve. Now, if you remember from a couple lessons ago when we covered the reciprocal identities, we learned that cosecant is the reciprocal function of sine. That means that cosecant is equal to 1 over sine. And that's going to be a very important fact that we're going to use today. So we'll circle back to this fact in a minute, but first we're going to take a look at our axes. So here I have already drawn out my x and y axis. Notice that I have offset the y-axis to the left so that I have a little bit more room so I can focus in on those first 2 periods of cosecant and the positive x-axis. Just like when we were graphing sine, cosine, and tangent, we need to go ahead and section out this x-axis, and I'm going to start by sectioning it out with pi over 2 increments. Cosecant is going to have the period of 2 pi, so I want to make sure that we make it all the way out to at least 4 pi on my x-axis. Alright, so it looks like I didn't actually leave enough room to get this out to 4 pi, so I'm just going to extend this axis a little bit more to make sure that we have enough room. Now that's really important that I get this all the way out to 4 pi, because if I want to show 2 revolutions of cosecant, cosecant has a period of 2 pi, much like sine. So I'll have one period between here and here, and then another period here. So that's really important. And then just for good measure, I'm going to show a little bit on the left-hand side of the axis. This is going to be negative pi over 2. And then much like our other graphs, we're just going to mark positive 1 and negative 1 on the y-axis. Now the easiest way to graph cosecant is to remember that it is the reciprocal of sine. And we're going to start by plotting those points for sine. And we're going to use those points, but we're going to connect the dots a little bit differently this time in order to make the cosecant graph. So one thing I'm going to do slightly different is when I go ahead and I put in my points, whenever I have a point that is on the x-axis here, instead of a point, I'm just going to put a little dash mark. And what that's going to do is that is going to be an indicator that I'm going to draw an asymptote at that point. And if all of that sounds completely foreign to you right now, that's okay. We're going to cover that in a second. So you just want to get started by filling in the points that you would if you were graphing sine. So remember, sine starts at 0, 0. And because this is on the x-axis, I'm just going to put a little dash mark here. Then sine goes up, comes back down to 0, down to negative 1, 0, and a little bit on the negative side here. I'll just go ahead, I'm at 0 here, so I would be going down to negative 1 at negative pi over 2. So what I've done is I've put in the points for the sine graph. Now as you can recall, the sine graph goes like this. All right, but what we're going to do here is we're not going to make a sine graph out of it. We're going to make the cosecant graph. So all of those places where I put the dash marks at pi intervals on the x-axis is where we're going to have vertical asymptotes. A vertical asymptote is an invisible guiding line, and it's going to show us the end behavior of a lot of places on our graph. So I'm going to explain more about this vertical asymptote idea, but first we're just going to draw them in. So they're not actually part of our graph, they're just a guiding line. So instead of putting a solid line, we're going to put a little dashed line to represent our vertical asymptotes. And I'm going to fill those in all these places where I put dashes. So those end up being the pi increments. All right, we're almost there. So the next thing that we're going to do is we're going to fill in these little cosecant curves. And cosecant is a discontinuous graph. So that means it's not one solid smooth curve like we had with sine and cosine. It's more like tangent, right? We're going to have all of these divisions where our curve never crosses. So these points that are left over from our sine graph are kind of the anchor points of our cosecant graph. So all I need to do here is draw a dish-like curve going up on each side, and what that's going to do is it's going to be bound by these vertical lines here. So this goes up and up and up and up, and it's going to continue like this, and it's never going to cross where these vertical lines are. So it's going to get infinitesimally close to those lines, but never cross. So the ones on the positive side of our axis are going to be going up. The points on the negative side of our axis are going to be facing downwards. So that's a really simple version of the cosecant graph. Now, if your teacher wants a more detailed version of the graph, what you can do is you can go ahead and subdivide each of these intervals, and that'll give you the pi over 4 increments. And you can go ahead and look up what cosecant of pi over 4 is, and 3 pi over 4, and so on. And that'll just give you a little better idea, a few more points that you can sketch on these curves to make them a little bit more consistent. As you can see here, mine kind of vary a little bit because I just have one point that I'm anchoring them down with. But if you just need a really quick sketch, I think that that's a good place to start. So that's your cosecant graph. And the last thing I want to show you is just where that invisible sine graph, that it's its reciprocal function, fits into this picture. Now this is not something you need to do if you were graphing the cosecant graph. I just want you to see how these two graphs relate, how cosecant and sine relate. So I'm going to go ahead and sketch in the smooth curve for sine because it's kind of an interesting picture. So that's kind of a rough sketch, but you get the idea here. Here is the sine graph, and it fits very nicely in between the cosecant graph here in dark purple. And you can see that whenever there is an x-intercept on our sine graph, that is where these vertical asymptotes fall, and all the peaks and valleys is where the cosecant graph shoots off from. So that's the reciprocal nature of these two graphs, and they work very nicely together. Now, when we move on to doing the secant graph next, you're going to see this exact same type of graph where the secant graph fits really nicely around the cosine graph because secant and cosine are reciprocals of one another. So it's going to be very familiar and very easy for you to graph the secant graph. Okay, so for this secant graph, I'm going to do the exact same start. I'm going to go ahead and section these out with pi over 2 increments. And I'll probably have to extend my axis a little bit further on the right-hand side here to ensure that I make it to 4 pi, which again will give me 2 revolutions. Alright, so now that I have my axes all sectioned out, I'm going to go ahead and plot the points for cosine. And that's because the secant graph is the reciprocal of the cosine graph. So we're going to use this important fact to draw in our graph. Once again, if I cross the x-axis with any of those points, I am going to put a dashed line to represent a vertical asymptote instead of a point that would represent a point on my graph. Remember that cosine starts high, it starts at +1. So my first point's going to be here. Then it's going to dip down in that same pattern where we go down, down, up, up, down, down, up, up. So all of these places where I put the dash marks, that's where I'm going to insert my vertical asymptotes. And as you can tell, this time instead of being on pi increments, they are on the half increments. So like -pi/2, pi/2, 3pi/2, 5pi/2, 7pi/2, and so on and so forth. So just like with our cosecant graph, these vertical asymptotes are going to serve as our invisible guidelines for our secant graph. And all of these points that we have remaining here from our cosine graph are going to be the anchor points for our secant graph. And just like it, they're going to curve up and down, up and down. So you're going to go ahead and fill those in. Again, just like I said in the last one, if you need more points, if this is not enough points, you can go ahead and section these out and look up those points on the unit circle and get a little bit more detailed of a graph. So here I have my secant graph, and as you can tell, it is a lot like my cosecant graph. It's just shifted over a bit. See how here my first curve was to the right of the axis, and here this first curve splits the axis. So much like how sine and cosine are essentially the same graphs, just shifted over a bit, so are cosecant and secant. And just like our cosecant graph, I can go ahead and connect the dots and fill in the reciprocal function, which would be the cosine graph for secant. And I'll go ahead and do that now just so you get a nice little picture and a good memory aid to remind you that yes, the secant graph fits very nicely around the cosine graph. And the last thing I want to point out with the secant is exactly where your two revolutions are. So the typical way that they're described is going from 0 to 4 pi. That is 2 revolutions. So you can see here that 1 revolution would be right here. So it's the dark purple graph. Remember, that is our secant graph. I just drew this light purple cosine graph so you can see how they relate. So it's just this part, and half of this part that makes 1 revolution of secant. And if I go here, I have the same picture over again with a half up, full one down, half up. So from 0 to 4 pi, that covers my 2 revolutions of the secant graph. And of course, you can always sketch a little bit beyond that to give yourself a good picture and a reminder that it goes on forever in both directions. For our final graph today, we are going to graph the cotangent curve. And remember, it is the reciprocal of the tangent curve. And much like the tangent curve, it's going to have a period of 1 pi instead of 2 pi. And it is going to have vertical asymptotes in a similar shape, but it's going to be oriented a bit differently. So the first thing we want to do is section out our x-axis. I'm going to start by breaking this into pi/2 increments. unlike the secant and cosecant graphs, unfortunately, with the cotangent graph, we can't just plot the points of our reciprocal function and then use them to graph the cotangent function, because the cotangent function doesn't really reuse the same points in the way that secant and cosecant do. So instead, we're going to have to plot some new points. And I think the easiest way to remember these points is to do a little tiny miniature version of the unit circle just at the pi/2 increments to start with. So here's my teensy tiny unit circle, and I'm just going to go ahead and mark what the points are on the 4 axes. The reason I'm doing this is because we are going to generate our points on this graph by simply looking at this simplified unit circle. So remember, we said that cotangent is the reciprocal of tangent. Another way to think of that is that if tangent is sine over cosine, then cotangent is the opposite of that. So cotangent is cosine over sine. And remember that our cosine is represented on the unit circle by the x-coordinates, and our sine is represented by the y-coordinates. So I could go ahead and find the points at 0, pi/2, pi, 3 pi/2, and so forth by simply dividing x over y at these places. So let's go ahead and do that. So let's start with 0 on our x-axis. So 0 here, I have cosine of x, so x is 1 divided by sine, which is 0. So 1 divided by 0, well, that's undefined because I can't divide by 0. And whenever you get an undefined solution, that means you have a vertical asymptote. And if I failed to mention that in the first 2 problems when I was talking about vertical asymptotes, then that's a really important point for me to mention now, that all of these places on the secant, cosecant, and cotangent graphs where we have these vertical asymptotes, it's because we have divide by 0 errors. That doesn't mean that all vertical asymptotes are divide by 0 errors, but it does pertain to all the ones that we're working with today. So I'm going to go ahead and put in a vertical dashed line at 0 radians. Now at pi/2, I take 0 and divide it by 1 and I get 0. So I'm going to go ahead and put a point at 0. At pi radians, I get -1 divided by 0. So I'm going to go ahead and put in a vertical asymptote. 3 pi/2, I have 0 divided by -1, which is 0. 2 pi, now I'm back at the beginning and I already know that I had a vertical asymptote here, so there's another vertical asymptote here. 5 pi/2 is the same as pi/2, so I'll have 0. 3 pi is the same as pi, so I'll have a vertical asymptote. And let's jump on over here to the -pi/2. Remember, a negative radian means a backwards turn, so I'm going to go backwards pi/2 radians, and that gets me to 3 pi/2. At 3 pi/2, I had 0 divided by -1, so 0. All right, so that's not really enough points to actually tell what the cotangent graph is doing. So what I'm going to do now is I'm going to add in the pi/4 increments, which will just be splitting the distance between each of these markers I already have. So now, because we want to figure out what these points are, I'm going to go ahead and add that into my unit circle. So those are just going to be the pi/4 or the 45-degree angle triangles inside my unit circle. And now I'm just going to fill in those little points. So here it is square root 2 over 2, square root 2 over 2, because remember, these are 45, 45, 90-degree right triangles, and so we get the same legs. Now I just can take this same ratio and copy it in these other spots and just add the negative signs whenever I'm going left or down. So that means that this one would be negative square root 2 over 2 because I'm going left on the x-axis, and then positive square root 2 over 2 for y since I'm going up. This point will be both negative square root 2 over 2 on the x-axis and negative square root 2 over 2 on the y-axis, since I'm in the third quadrant. And then finally, this point right here will be a positive square root 2 over 2 on the x and a negative square root 2 over 2 on the y. All right, that's a little bit hard to see because I have a lot going on right here. So I'm just going to circle these 4 points because those are the ones we're going to be working with. So you can kind of see it a little bit better. So here I have pi over 4. And at pi over 4, which would be this angle right here, I see that I have square root 2 over 2, square root 2 over 2. Now remember that cotangent is the x over the y, so when I divide something by itself, I'm just going to get positive 1 out. So here I can put a marker at positive 1. The next one is going to be 3 pi over 2 right here. So 3 pi over 2 is here. And I see that when I divide x by y, I'm going to get negative 1 because I have a negative square root 2 over 2 divided by a positive square root 2 over 2. And because the cycle of cotangent is simply pi, this picture is going to repeat itself here and so on and so forth. So I know that here I'll be back up at positive 1, here I'll be at negative 1, positive 1, negative 1. And on the right-hand side, this point right here will be a negative 1 as well. Okay, so now I can go ahead and add the shape. So now we have the cotangent curve sketched. It is the exact opposite direction of the tangent curve, and it's shifted over a tiny bit. So although it looks pretty similar, it's slightly different. It, like tangent, has a period of pi. So this is one picture, this is 2 pictures. So if you needed 2 revolutions, that would be a good picture. Here is a 3rd revolution, and here's the start of another revolution on the negative side. So that pretty much sums it up. It is always a bit of a challenge to get the correct shape in here, but just do the best you can. If you do need to look up more points in order to get a better shape, then that's perfectly okay to do. You can use the unit circle, you can use a reference table, or you can even use your calculator to get a better idea for these graphs. But the main point in all of these here is to know the parent functions and the important points on these graphs, because as we move into the graph transformations and you're shifting, reflecting, and stretching and compressing these graphs, you need to know where the starting points are.